So in this video, we're going to do three things. We're going to derive equations for kinetic energy and gravitational potential energy from work done. We're going to, secondly, define power and efficiency when we're looking at energy transfers. And lastly, we're going to use the idea of energy conversions to solve more complex questions. Right, we're going to see if we can derive the equation a half mv squared from the expression for work done. Well, where does work come into it? Well, when you do work, for example, in moving an object in such a way that it gains velocity. So if you're pushing this piece of furniture in a straight line, it will gain a velocity v. That means that you are converting your chemical energy from your breakfast into kinetic energy. Now, how are you doing that? You are doing work. You are applying a force and it is traveling a distance d. So that means the work that you do, force times displacement, will be equal to the kinetic energy eventually gained by the piece of furniture you're moving. So this is the beginning of our proof. F times S, force times displacement, equals kinetic energy. But what do we mean by kinetic energy? Let's have a look. Force is also equal to mass times acceleration. So therefore, work done, force times displacement, is also equal to mass times acceleration times displacement. Not bad, but we're still not at a half mv squared. What's the next step? See if you can guess. If we apply the equations of motion at this stage, what we can find is the following. If v squared minus u squared is equal to 2as, and the initial velocity is 0, then what we're left with is v squared is equal to 2as. Now, if v squared is divided by 2, will be left with as on its own. So as is now equal to v squared over 2. So we can replace the acceleration times displacement part here. We can replace that with v squared divided by 2. And that gives us our equation of a half mv squared. So we have derived an equation for kinetic energy using F equals ma and v squared equals u squared plus 2as. I hope you followed that. Let's do the same with gravitational energy. It's actually a little bit more straightforward. This time the work is done in raising an object. So you are lifting an object up a height h by doing work. So the force times displacement would be the weight, because you have to use a force equal to the weight of this object in order to lift it, right? So your force would be equal to mg. And your displacement would be the height that you're lifting the object to. So in the end, the gravitational potential energy is equal to the work done, but that work done can be expressed in terms of the mass, g, which is equal to 9.81, times height. And there you have the proofs for kinetic energy and gravitational potential energy. Let's look at power and efficiency. Power and efficiency allow us to compare systems and to judge how much energy is being used per second or transferred per second, and look at basically how effective that energy transfer is in terms of the useful energy and not so useful energy. Energy changes are not always perfect, and they always involve energy losses. But this idea of an energy lost goes against energy conservation, right? So energy cannot be created or destroyed. That was the rule that we learned about in the first lesson. So what was actually happening to this energy lost? It's actually being transferred into less useful types. Energy is always conserved. So what we do in order to assess how much useful energy we're getting, we look at the efficiency. Now this is a Sankey diagram. We'll be learning about these in topic 8, but they allow us to visualize the energy in and then consider how much useful energy is coming out. Here we can see that a light bulb has 100 joules of electrical energy coming in and only 10 joules of light energy coming out. The other 90 joules are wasted. Well, they're not wasted, they're just being transferred into a less useful type of energy, heat energy. Petrol stations, coal-fired petrol stations, and in fact, pretty much most electricity generating installations are just as useless or inefficient. Here we have the chemical energy coming in, and we can see just how small the amount of electricity or electrical energy that finally comes out compared to all that energy which is less useful. So this would be about 30% useful. This would be 0.3. If this is 1, this is 1, this would be 0.3, and this would be 0.7. All the energy that's transferred to less useful stuff. And here we have another diagram for a car engine, a petrol car engine. Hopefully a thing of the past soon. For every 200 megajoules of energy that comes in, we're only getting 80 megajoules of mechanical energy out. The rest is less useful. So efficiency allows us to calculate this as a percentage. Efficiency is the ratio of the useful energy out over the total energy input. And you can interpret that in terms of work as well. So if we go back to our original Sankey diagrams, the efficiency of this light bulb would be 10, the useful energy, divided by 100, which is the original energy, to give us a 0.1, which we then multiply times 100 to give us a percentage. And that's how we would work out, efficiency as a percentage, right? The ratio of the energies times 100. So what's power? Power is the rate of energy transfer. So when you have these changes of energy from chemical energy, in this case, to mechanical energy, or in a speaker, for example, you've got some speakers here from electrical energy to sound energy. These are energy transfers, and we can calculate the power by finding out how long it takes for that energy transfer to take place. So we've got power equals energy over time. That gives us a power rating. And you can see these power ratings on all types of appliances. They're called wattage and wattage. The units of power are the watts, right? So W-A-T-T. And you can see them here on these speakers. But you can, pretty much see them on all light bulbs, speakers, things like that. They tell you how much energy in joules per second. So this light bulb is transferring 60 joules per second of electrical energy into light energy. This one is converting 30 joules of electrical energy into sound energy, etc., etc. And so power equals the work done, the energy transferred, or just as valid, the work done, or it could be the change in kinetic energy. It could be any kind of energy up here, really. However, whatever energy type we're considering, divided by the time taken. Okay, this equation is not given in the physics data booklet. There is a simplification or a derivation which is, however, and that's to look at work done, if you remember, was force times displacement. So if we substitute that in, force times displacement, or change in displacement, divided by change in time. And what we're doing here is we've just expanded our definition of work to include force times displacement. And if we now take this part of the equation, change in displacement over time, change in displacement over change in time, we get velocity, okay? A constant velocity. Remember, this idea of velocity equals distance over time only works if you have zero acceleration, right? So once we substitute this in, delta S over delta T, change in S over change in T. For V, we're left with this expression, which is power is equal to the resistive force, the force acting, times velocity, okay? And it's probably best to just apply this equation. It's at a bit of a loose end as a derivation, so we'll come back to it later. Okay, so I now need you to try the questions on worksheet 2.33, where you have to write some notes and try some power efficiency questions, and then have a go at these extension questions. Give you something to think about a little bit later. And then these questions are just to get you thinking about energy conversions a little bit deeper. And I think that's it for energy. Well done for coming this far.